Welcome back. Chemistry 3120, Advanced Organic Chemistry. Today we're going to continue our discussion on the Aldol reaction. We just finished cross condensations, which was lecture 14. We're going to focus our attention on the specific Enol equivalents in the Aldol reaction. I'm going to divide this up actually into two parts, part A and part B. So we'll do part A right now. So that will be lecture 15, and then 16 will be part B. So moving along our checklist, we've completed this and this. So this is lecture 15, specific Enol equivalents in the Aldol reaction. Okay, and as I mentioned, we'll call this part A. Okay, so as we've kind of talked about just last lecture, we learned that specific Enol equivalents are important for that directed Aldol approach. So using the correct Enol equivalent is key for understanding how to make the correct and desired product. And there's so many different types of specific Enol equivalents that we've learned. The last one we just talked about was Asan Enolates, but you also have things like silyl enol ethers, enamines. We'll talk later about something called zinc enolates. So when do we pick the right one and for which electrophile? Okay, so picking or using the correct Enol equivalent is key for understanding how to make the desired Aldol product. And as we've learned, we already know about lithium enolates. So lithium enolates, you can't make them from aldehydes because they self-condense. But ketones, you can do it, although it's a little tricky, but you can use those tricks that we talked about with esters where you keep the temperature low and you add this dropwise to a stirring solution of strong base. So in our case, let's use LDA. We'll keep that at minus 78, and we'll create our lithium enolate of the ketone. And then in step 2, we will add our enolizable partner. So in this case, this will be our electrophile. This will come and react here, and you'll get your desired product. Just want to point out too, that's phenol by the way, that the transition state, lithium bases are good also with aldol reactions because you can form this 6-member transition state between the oxygen lithium and then the electrons coordinating to that internal lithium before the workup. But the point I'm making here is that you don't mix A and B together. You first form the specific Enol equivalent. And then B, you add your electrophile. Okay, so that's how you would do this with a lithium enolate. Now let's talk about another specific enol equivalent that we've learned before. This is called silyl enol ether. Okay, so silyl enol ether. Who remembers how to make those? So let's say we have a ketone, and we want to convert this to a silyl enol ether. So that means we need to form a double bond here, remove an acidic proton, and form this oxygen silicon with 3 methyl groups attached. So a good way to do this, or fairly straightforward way, is to take triethylamine with TMS chloride, or trimethyl silyl chloride. And you can imagine the triethylamine will remove the proton, form an O-, and then the O- will come and react with the silicon, displacing off the Cl. And this is your silyl enol ether. This is a nucleophile, but it's weak, as you've learned. And you learned from chapter 25 that this is good for alkylating tertiary electrophiles in the presence of a Lewis acid. So if we are to react this with an electrophile, and I'll draw an electrophile right here. Let's use this as an electrophile. If you take that silyl enol ether and react it with this, nothing's going to happen. That's just too weak of a nucleophile. So we need to activate it and use the same approach that we learned with silyl enol ethers when we were undergoing alkylation with tertiary alkyl halides. So we can use Lewis acid like tin or titanium tetrachloride, and what that's going to do is that the oxygen electrons are going to be attracted to that positive metal center. And you'll generate an activated aldehyde that is now quite prone to electrophilic attack or nucleophilic attack at that electrophile. So now your silyl enol ether is in a good shape to come down and attack the electrophile like I'm showing. So what does that look like? So let's draw it out. I will just draw out the actual TMS. You'll see why in a second. Okay, so we'll generate an intermediate like this. You can see here that the titanium is negatively charged. It would really rather be neutral. And what's going to happen is that this bond is going to break, titanium will go out, and you just need catalytic amounts so it can go out and search another aldehyde molecule. But the electrons from here will transfer to the silicon and break this oxygen-silicon bond because you have this oxonium ion, and the oxygen would rather be neutral. So you're going to get transfer electrons here, and then making that neutral. Generate this compound here, and then during your workup step with this Aldol reaction, what we're going to do is we're going to add water, and then water will come react at the silicon. You'll pick up a proton from water on the way out, and your final product will be this compound here. So again, using a silyl enol ether to generate this product here. And just to recall, we can't just add these two together, throw in base, and expect to get this product, because you know that this is more electrophilic. This will enolize, and you'll get this reacting with itself. You might also get a combination of this enolizing and reacting there. So you get a mixture of different products. Whereas if you use this specific strategy, you'll get the desired product. Okay, so just to note that silyl enol ethers are weakly nucleophilic, but they react well with aldehydes and ketones. In the presence of a Lewis acid. Titanium tetrachloride or tin tetrachloride are good ones. All right, let's go through a retrosynthesis. We did that last lecture. Let's try it again. All right, so let's synthesize the following compound. So I'll give you a second to write that out, and then I want you to think of what your units are going to be, and then we've got to think about how we'll put it together and what strategy we'll use to synthesize it. So I'll just give a few seconds. I'm going to grab some water. I'll be right back. Okay, so this is your carbon-carbon bond, and it's dehydrated. So before it got dehydrated, you had a hydroxyl group, you had a hydrogen here, and therefore, if that used to be an alcohol group here, this must have been a carbonyl. So this portion here is your nucleophilic form. Okay, so that's going to look like this. That's your nucleophile when it becomes an enolate or a specific enol equivalent. And your electrophile will be everything on this side of the molecule. So you had an OH here after it got attacked. So before it got attacked, it used to be carbonyl, and therefore it must have been an aldehyde. If you're having a little bit of trouble figuring out what the components are, go over through this part again and go back to the last lecture in terms of how we looked at how to identify step 1, carbon-carbon bond, step 2, what does a hydrated aldol look like, and then unraveling what the electrophile and nucleophile are. Okay, so once you determine what these components are, now we can figure out the best way to put them together. So if you mix these two together with base, it's not going to work because this will just self-condense. This will also react there. So this is the only exclusive compound and product that we want to make. So what's the best way to do that? So we can take our nucleophile, but we have to convert it to a specific enol equivalent. So we could use a couple of different ways. We could use the Asan Enolate method that we learned last lecture. So we can convert this to first an imine by using a primary amine, primary plus catalytic protons, then a strong base like LDA, and then adding your electrophilic component, and then doing the water workup step. So that would work. That would work quite nicely. Now, I just want to mention that LDA, it's a great base, but it's not the easiest thing to handle because it's such a strong base. And if researchers can avoid using LDA, we will avoid using LDA. As I mentioned, it's unstable, it's expensive, it's not the most practical thing to work with. You have to use typically low temperatures. So another way to make this compound, okay, so that's approach A. Another approach would be to convert this using our Asan Enolates strategy that we just learned. So this molecule here, we want to create an enolate at that carbon. Now, because it's symmetrical, we don't need to worry about which side we're going to enolize from, so that's pretty handy. So we can actually take triethylamine with TMS chloride to generate the silyl enol, and then we now add our electrophile. And as I mentioned before, if you react these together like that, nothing's going to happen, but you have to add your titanium tetrachloride to activate that so you get that reaction to happen, because silyl enol are weakly nucleophilic. And then lastly, you'll have your water workup step to remove that silicon from that oxygen, like I'm showing you there. And then you'll want to heat this up too, also in this case here, so you get your dehydrated product. Okay, so two different approaches, and they work quite nicely. I just want to mention verbally that the enamine approach that we learned, that is taking a secondary amine and converting it to an enamine, actually doesn't work well with Aldol reactions, mainly because the enamine itself is weakly nucleophilic, and there isn't really a good way to activate the electrophile using that method. Okay, I'll summarize and talk more about that in a little bit. Okay, good. So let's synthesize another similar derivative to that one. Okay, let's synthesize two similar molecules here. I believe they're isomers. Okay, so one of them is this one here with a methyl group, so we'll call that A, and then B will be okay, so synthesize these compounds, again using aldol of course, and let's take a look first at how we're going to break these up into our key building blocks. So let's start with A. You can see that these are not dehydrated. That's your key carbon-carbon bond. So everything up here is your nucleophile. And then this is your electrophile. It's a single carbon. Okay, so there's actually another hydrogen there. Single carbon with an OH group. So what was it before it got attacked? Well, there are two hydrogens adjacent to it. Therefore, the electrophile is formaldehyde. This is a very strong electrophile. Okay, so how are we going to mix these and make these react using our specific Enol strategy? All right, so let's take our nucleophile. We need to enolize specifically at this position. You have a few different protons, right? You have alpha protons here and here. If you generate an enolate here, that's your thermodynamic enolate. If you enolize over here, that's your kinetic enolate. Triethylamine, that's a weak reversible base. So you're favoring thermodynamic conditions. So in order to generate the desired silyl enol ether, we can simply use the conditions we've been using previously. So triethylamine TMS chloride. That generates our silyl enol ether, and then this will react with the formaldehyde in step 2. And I just want to make a note that with formaldehyde, compared to like acetaldehyde or any other aldehyde, formaldehyde is just incredibly electrophilic. We'll actually talk about this actually when we talk about enones during a specialized reaction called Mannich reaction. But it's just so electrophilic that the only time when you're using a silyl enol ether and you do not need to use Lewis acid like titanium tetrachloride is when you're using formaldehyde. Okay, so this is the exception, and I'm showing it to you now. So when you do this reaction, this will react appropriately, you'll get the reaction, and then you hydrolyze that with water, and you'll generate the desired product A. Okay, very good. If we want to make compound B, which is similar, except you now are using the nucleophile from this carbon here, let's go back to the drawing board and think about how we'll remove these protons. So the way we'll remove those protons is we want to use a sterically hindered base. The pK of these two are essentially the same. They're non-distinguishable. So a great base that we've learned about that's sterically hindered, that's non-nucleophilic, is LDA. So you're going to use LDA, not on that compound, that's what we want to make, but on this compound. And again, you got to use that trick so it doesn't self-condense, and you add it, slowly to a stirring solution of LDA, and then you'll generate your enolate. Now, as I mentioned, these enolates are quite reactive. So in order to take that enolate and convert it to a silyl enol ether, you do it over 2 steps. First, kinetic enolate formation, and then 2, TMS chloride. You can think of it like a protecting group. This will just come and react, and now you have a stable silyl enol ether at the kinetic nucleophilic position. Very convenient for our case here. And then, at a later stage, you do the same thing. You add at step 3 your formaldehyde and then do a workup step. Okay, but the approach is a little different because you need to control with this asymmetric ketone which side you'll react on and how to do that. So your product will be B, which is over there, and I'm just redrawing it again. Yeah, what else did I want to talk about? Well, it's always good to go over pKa's. Remember, these have pKa's of 20. All right, so your LDA has a pK whose conjugate acid is 36, so it's irreversible. With triethylamine, when you actually do this reaction, you generate triethylamine plus, that's protonated. The pK of this is around 10. So it's a reversible base, but you let that sit for a while, and you can imagine once you get a little bit of that enolate form, it's going to react with a TMS chloride, and using Le Chatelier's principle, then a little bit more will come and react. So you can generate very good and high quantities of that without an irreversible strong base. Good, good, good. Okay, so write that down. I'll just do some erasing. On the topic of things like pKa, let's take a look at this 1,3-dicarbonyl species. And what would happen if we react this with sodium methoxide and ethanol? Specific equivalents from a 1,3-dicarbonyl species. So if you mix these two components together with sodium methoxide, you might be saying, oh geez, not again. This is going to just self-condense because aldehydes are just so much more electrophilic and reactive compared to esters. Okay, so you can imagine this will just get picked up. Now the pK of this compound here, as we've talked about many, many times, is 20. Right? But what is the pKa of these protons here that are wedged between two different esters? This one here is much lower. It's around 13. So in terms of acid-base chemistry, because the difference here is greater than 3, it's actually 7, around 7, your sodium methoxide will generate exclusively this enolate, and then this enolate will react only with this electrophile because it's much better. So in this case, you're only going to get one distinct product due to the inherent differences of pKa. All right? If this were just a regular ester without another, if it weren't a 1,3-dicarbonyl species, then it'd be a completely different story. Okay, so that will react, and then after some dehydration, will generate this compound. Okay, so this corresponds to A, this is A, so based on large pKa, based on large pK differences between the aldehyde and 1,3-dicarbonyl species, product A is formed. And you can put that together in one pot. It's always good to go through some example reactions. Let's take a look at this compound, and if we treat this with TMS chloride, triethylamine, and then treat this with this dicarbonyl compound, what's the product going to be? And conversely, if we treat this with LDA, what will the product look like? All right, so let's start with the one on the left. So LDA will remove this proton, sterically hindered, and then that enolate negative here will react with this molecule. You have a ketone and an aldehyde. The aldehyde is more electrophilic, so here's your key carbon-carbon bond connection right there. And then you work it up to form your aldol product. So that will look like this. And then conversely, on the other side, you take this same starting material, make a sal enol ether, thermodynamic conditions, you form it through this nucleophilic sal enol ether, react it with this aldehyde. You need to use titanium tetrachloride, then work it up. So you're going to now get reaction occurring at here, and that will look like this. All right, so I'd like to just spend a few moments just summarizing what we've learned when we're using specific enol equivalents and aldehydes. So I think by now I don't need to convince you. If you take, let's say, two compounds like this, two aldehydes, either acid or base, if you mix these two together, you'll generate a combination of different products. This will self-condense, this will self-condense, this will react here, this will react there. 4 different potential products. So we can control that using specific enol equivalents. So we've learned about lithium enolates. We've learned about silyl enol ethers. Lithium enolates you can't use because you just know that with aldehydes and lithium enolates, that's not an appropriate solution because you'll just get self-condensation. Aldehydes are just too electrophilic. If you want to use silyl enol ethers, Sure, no problem. Right, so you need to use something like triethylene TMS, then use the electrophilic aldehyde with titanium tetrachloride or tin tetrachloride. Enamines. We talked about enamines very briefly, but it turns out that enamines, if you take an enamine from this aldehyde and you use a secondary amine, it's weakly nucleophilic, and you can't use Lewis acids to help promote this reaction with an electrophile, because actually the nitrogen tends to coordinate with that Lewis acid and mess things up. So enamines are just in general not a good viable approach when we're thinking of aldehydes and using specific equivalents. Then lastly, we looked at Asan Enolates. Yes, we can use Asan Enolates. Use a primary amine and catalytic protons, then use a strong base like LDA, and this will generate your Asan Enolate, which is strongly nucleophilic. And will react well with that electrophilic aldehyde. So in general, for cross condensations, of aldehydes with the Aldol reaction, use either a silyl enol ether or Asan Enolate approach. Okay, so that's it for this lecture, number 15. Stay tuned for part B. See you soon.